Hello, my name is RD and we are going to solve this problem 4.75 from Nilsson and Riddle book. So the question is find the Norton equivalent with respect to terminals AB for the circuit seen in figure P.75. So I will take this step here. So the first one is to find out the open circuit voltage AB, or that is the Thevenin voltage, right? And then the second one is to find out the short circuit current in AB. So we will have the Norton current, find IN. And then finally, we can get the Norton resistance or Thevenin resistance that is the same with using Ohm's law, which is VTH divided by IN. Okay, so now let's do it step by step. The first one is to find the VTH, which is the same as the open circuit VAB, which is this one. So we'll have plus minus here, VTH is here, and let's set this node here as our ground. So the voltage here will equal to 0. Good. Now let's name this node here as VA. Okay. And this node here as VC, because we already have B here, right? So let's just name this as VC. And the current, I just follow this one. So we'll have this, and I just assume this is going down. This is going to the right, and I just follow this current source for this branch. Good. And then what do we know? Again, we have 280 volt here. 280 volt, because this is 280 volt from the ground. Okay, now let's do KVL, no, not KVL, KCL at VC. KCL at VC. KCL said that the sum of the currents that goes in will equal to the sum of the currents that goes out. Okay, and the only current that goes in here is this one here. So we'll have 280 minus VC divided by 2 here. And then for this one, we will have VC divided by 2. VC minus 0, which is VC, divided by 2. And then this one here, we will have plus, we will have VC minus VA divided by 2. And then for this branch, we have 0.2 I delta. So we will have plus 0.2 I delta. What is I delta? I delta is this one. So we will have this value, which is 280. Oh, I ran out of space. Let's move this slightly to the left. Okay, we will have 280 minus VC divided by 2. Good. And I think we can just cancel out all the 2, right? Because we have 2 on the left hand side and 2 on the right hand side on the denominator. So we'll have 280 minus VC, and then we will have VC plus VC minus VA, and then plus we will have 0.2 multiplied by 280. And what is that? 0.2 multiplied by 280 is 56. So we'll have 56, and then we will have minus 0.2 VC. Good. Now let's do some simple math here. Let's move this 56 to the left hand side. So we'll have 280 minus 56, and then we will have 3 VC minus 0.2, that will be 2.8 VC. 2.8 VC, and then minus VA. Okay, let's simplify things. So we will have let's just do minus VA plus 2.8 VC, and that will equal to 280 minus 56. This is 56. 280 minus 56, that will be 224. 224. Good. Now let's save this as equation number 1 because we need two equations to solve this. Okay, let's clean up that and move on. Okay, now let's do another KCL, which is on the node VA. KCL at VA. KCL said that the sum of the current that goes in will equal to the sum of the currents that goes out, right? And so the currents that goes in is this one. We have 0.2 I delta, and I delta is this one, so we'll have 280 minus VC divided by 2. Good. And then we will have this one here, so we will have plus VC minus VA divided by 2, and that will equal to VA divided by 5.6. Okay, now let's do some simplification. How to do some simplification here? Okay, maybe let's just multiply both sides by 5.6, or okay, let's just multiply this inside. So we will have 0.2 multiplied by 280, that is 56, and then minus 0.2 VC divided by 2, and this one we will have VC minus VA divided by 2, and that one will be VA divided by 5.6. Okay, now let's multiply both sides by 5.6, which is very strange number here, but okay, let's do that. 2 and 5.6 will cancel out into 2.8, right? So we will have 2.8 multiplied by 56, and then minus 0.2 VC, and then plus we will have 2.8, we will have VC minus VA, and then we will have VA here. Good. Now let's again distribute all things. 2.8 multiplied by 56 is 2.8 multiplied by 56 is 156.8. 156.8, and then minus, what is this? 2.8 multiplied by 0.2. 2.8 multiplied by 0.2 is 0.56. Okay, 0.56, and that is VC, and we will have plus 2.8 VC, and then we will have minus 2.8 VA, and let's move this VA to the left hand side, so we will have minus VA, and all of that will equal to 0. Good. Let's put some separator here. Okay, now minus 2.8 minus VA, we will have minus 3.8 VA. And then 2.8 minus 0.56, that is the task of calculator, which is annoying actually. Very bad number. Then plus 2.8. Okay, we'll have 2.24, so we'll have plus 2.24, and then let's move this to the right hand side. We'll have minus 156.8, and we have this as our second equation. Okay, oh, this is VC here. How to do some, yeah, okay, have VC here. So we have two equations with two variables. We should be able to calculate VA and VC, and that is exactly what we need because VAB here is equal to VA. Okay, and let's put that into calculator. Let's set our calculator as equation solver. Set up number 5 and two variables is number 1. Okay, let's plug this in. So we'll have minus 1 and then 2.8 and then 224. Good. And then the second equation is minus 3.8 and then 2.24 and then minus 156.8, which is very nasty number. Okay, so we will have PA is 112. Okay, that is a nice number. So we'll have PA is 112 volt. And what is PC? PC is 124. Okay, that is a nice number here. So our VA here is 112 volt. Good, so we'll have our Thevenin voltage here, which is 112 volt. Good, and that is just our first step. Okay, let's move on to the second step. So the second step that we need is to find out the short circuit voltage or I Norton between A and B. So this is our IN, right? So we will have to find IN. Find IN. Good. But I need to simplify the circuit here because this is shorted. All the current will pass through here and not here. So we can just delete this 5.6 ohm, and let's exactly do that. Okay, let's do it like this. So we have our simplified circuit here, and remember this is not A, and we shorted this. Good. B. And so we will have IN is this one here, IN. Okay, and I think the easiest way to do this is by using mesh analysis. Okay, let's name this loop as I1, and let's name this loop here as I2, and let's name this loop here as I3. Okay, let's see what can we get from this circuit here. IN is equal to I2, right? So our target is to find out I2. And then another things to note is I3 is equal to 0.2 I delta. But in this case, I delta is the same as I1. So we will have I3 is equal to 0.2 I1, which is very important value later. Okay, so now let's do KVL at I1 and I2. So we'll have KVL at I1. Okay, KVL said that the sum of the voltage in a loop will equal to 0. Okay, let's start from this voltage source, and because the current is flowing from the negative terminal to positive terminal, our sign will be negative, right? So we will have minus 280 and then plus 2I1. Okay, because this is 2 ohm 2 kilo ohm resistor. And then plus we will have I1 minus I2. All of that will equal to 0 because we already have all the three components, right? This, and this. That become this, and this. Okay. Now let's simplify things. 2 plus 2 is 4. So we'll have 4I1 and then minus 2I2. And let's move this 280 to the right hand side. So we'll have 280. Let's have this as equation number 1. Good. And now let's do another KVL, but this time at I2. Let's do KVL at I2. KVL said that the sum of the voltage in a loop will equal to 0. Good. Now we will have this one. So we'll have 2 I2 minus I1. Okay. And then we will have plus. Again, we will have 2 I2. But this time minus I3. However, I3 is 0.2 I2. So we will have 0.2 here. Not I2, I1. So we'll have I1. Good. And we only have two components here, right? So all of that will equal to 0. Good. So now we will have 2I2 and this is 2I2. So we will have 4I2. 4I2. And then we will have minus 2I1. And then minus 0.2 I1. All of that will equal to 0. And now we'll have minus 2.2 I1. And then plus 4I2. All of that will equal to 0. And this is the second equation. Okay, now we have two equations with two variables. We should be able to solve this, right? Using calculator. So let's do exactly that. Let's reset our calculator. Okay, and set up it as equation solver, which is number 5. Two variables is number 1. And let's plug this in. We will have 4 minus 2 and then 280. That is not 20. 280. Okay. And then we'll have minus 2.2. Good. And then 4. And then 0. So we will have I1 is this one, 96. I1 is 96 point what? 55. And the unit here is in milliampere. And what is I2? I2 is 53.10. Okay, so we'll have 50 what? 53.10 milliampere. 53.10 milliampere. Okay, so what is IN? IN is I2, so we will have 53.10 milliampere. Good. So here we have the Norton equivalent, 53.10 milliampere. Okay, we still need to calculate the Norton resistance. Let's clean these things up. Okay, now we can just calculate Rn by dividing VTH, which is 112 divided by 53.10. So that is the task of our calculator. Let's reset our calculator and divide them. We'll have 112 divided by 53.10. Okay, so we'll have 2.10. 2.11. Yeah, let's whatever. 2.11. And the unit is the volt divided by milliampere. That will be in kilo ohm. Okay. So now the Norton circuit is like this. We will have a current source, which is this one, 53.10 milliampere, and then the resistor here is in parallel with the current source, so that will be 2.11 kilo ohm. And then this is terminal A, and this is terminal B. And this is the final answer for this question. Hopefully I did not make any mistakes in my calculation. Thank you for watching. See you in the next video. Bye bye.